So now let's look at what we mean by efficient C code and look at some strategies by which we can actually get to write C code that is by some definition efficient. So the first thing, as I said, what do we mean by the term efficiency? It is a key term in the context of embedded systems, right? And it has many different variants or many different components to how you understand that concept of efficiency. We could be talking about something like resource efficiency, right? And what we mean by that is there are certain resources that are available to your computing system, the CPU or computation cycles of course being the first and foremost, but the memory very often turns out to be one of the most important constrained resources that you have available while constructing an embedded system. There are also things like the IO bandwidth, how much data can you get into and out of a system, right? Now, when you create an embedded system, you want to use these efficiently, and what that means is if a system has a certain amount of memory, then by all means go ahead and use all of it, but use it to the best way possible, meaning that you should not be restricted from writing a certain program because you used a poorly constructed data structure which occupied too much memory to start with, or you used the wrong kind of data type and ended up using up more memory than you should have, ending up with insufficient memory for some other actual data that you needed to store. Okay. Now speed essentially usually boils down to making the best use of the available CPU instructions. And what this means is there are, for example, processors that have CPU instructions that can directly, for example, update a value in memory, right, maybe increment by 1. Using that versus loading a data from memory, adding 1 to it inside a register and then storing it back into memory, it seems quite clear which one would be more efficient. Of course, it depends on the hardware. The hardware would have to support something like that. But knowing what kind of hardware you have, what kind of CPU instructions you have, and then using them in the right way contributes to what we term as efficiency. There is a concept of power efficiency which basically says, am I using more power than I need in order to run the system? And very often, for example, let's say that we have a device that we are building that needs to communicate over the network and it's using, let's say, Wi-Fi, right? Wi-Fi tends to be a power hungry network communication protocol because it has to keep waking up, transmitting beacons and so on. Whereas there are other protocols like Bluetooth which have better low power modes. In other words, it can actually go into kind of a sleep mode and wake up at a much lower frequency than what Wi-Fi would, and therefore has a better profile in terms of the power that gets consumed over a period of time, which finally translates into the total energy that the system is burning up. And one other dimension of efficiency comes down to just the code maintainability, right? Especially in contexts where this is something that needs to be maintained and possibly updated over time. Even just how well is it written and how easy is it for someone else to understand and update the system can have a significant impact in terms of efficiency. So you can sort of see from this that it's not like it's not a formula that you can just apply and say, hey, this is efficient or this is not efficient. This is slightly subjective in the sense that there are a number of different variations that you can encounter while actually looking at the efficiency, the concept of efficiency in an embedded system. But all of these are things that you need to recognize, understand, and be able to measure in the system that you build. Now, why does efficiency matter? Very often embedded systems tend to be very long running, right? And I've used the term fire and forget over here in the sense that these are things that you just pretty much start, and once you start them, you expect them to just run forever. You don't really want to keep checking on it or restarting the system or shutting it down. There is no concept very often of shutting down a system. Think of something like the control logic for an elevator or a lift, right? It's supposed to run 24/7. It's not doing a whole lot of work, but any time, day or night, somebody comes and presses a button, it should just respond. There is no question of running out of memory or the battery having drained. Nothing of that sort should ever happen. Any time that somebody comes and presses a button, it's supposed to respond. Okay, so this is what write once, run forever kind of behavior means, right? And in such a scenario, for example, you can't have something where you need to restart the elevator once every day or do something else to flush out the memory and make sure it doesn't have any problems. You may also want to minimize the system cost. This is absolutely important, and the cost itself can have multiple dimensions of its own. The first might be just the development cost, meaning that sometimes you might be willing to choose a particular set of components just so that you can get going fast, right? But then comes the deployment. You actually want to deploy it at scale, you want to release multiple of these systems, and the deployment cost starts to matter. And then eventually you might have some kind of a maintenance cost, which means that over the lifetime of the system, how often do I need to upgrade it? Do I need to change anything in it? Are there things that I need to alter or modify? All of those contribute to the overall system cost. And finally, efficiency also has a very important role just in terms of the performance of the system, right? Especially in real-time applications like automotive or other safety critical applications, you want to have code that is as efficient as possible, because you at no point do you want it to fail because it was not able to run fast enough. So there are a number of different strategies that we can use in order to improve our chances of getting efficient code, and we are going to look at a few of those strategies over here. The first and foremost would be the use of what I call memory efficient data types, right? And the basic idea is ensure that the data storage does not consume more memory than necessary. Right? This is especially critical in systems with limited memory. And an example of that would be, let's say that you know that your data are only 8-bit values, right? It might be that you are actually sampling data coming from an A to D converter, and the A to D converter is only 8 bits in size. Then, well, go ahead and use an 8-bit integer data type in order to store the value. Now, what happens if your ADC is a 10-bit value, right? That becomes interesting because very often you do not have a 10-bit data type in C. Then you have to think about it. What should I do? Should I discard 2 of the bits? Or should I just promote from 10 bits to 16 bits? Or should I try and group a few of these 10-bit values, maybe 5 of them together, right? So that I get 5 8-bit values, right? So there are many different options that you can sort of think about when you are dealing with data types that are not of a standard size. But the basic concept that we are trying to say over here is, don't use something that's unnecessarily larger than required. For example, taking an 8-bit value and storing it in a 32-bit integer, which would be the default, by the way, if I just declared everything as int, right, is probably a waste of space, especially if you start declaring arrays of such values, where the overhead just gets multiplied by the number of such values that you are storing. Similarly, when you have for loops and so on, you could very often find that the loop index could probably be a smaller data type, something like an 8-bit integer or a 16-bit integer. Now, this is a little bit tricky because most of the time the index in a for loop is not really stored in memory, so it's not like you are saving very much there. And in fact, what you might find is that just by having it as a 32-bit value, it gets stored into a regular register in memory and just gets used as a register. And there you might actually find the opposite problem, that trying to treat it as an 8-bit value makes it worse, because now extra logic is required in order to find out whether it has overflowed across the 8 bits rather than just treating it as a 32-bit value and saying, hey, let it just run for the number of iterations that it needs to. Okay. So the obvious benefits are, it reduces the amount of memory used and is especially beneficial in smaller and cheaper microcontrollers. Now, as we will be seeing later, right, there are many scenarios in embedded systems where we want to use global variables, primarily because we have sensor values or some other kind of parameters that are used in various different parts of the code. Now, the problem with those global variables is that they occupy a fixed amount of memory, and more importantly, they are there forever, right? From the time that you start the program until the time that you switch off the system, a global variable is occupying memory. So for a long running system, if you have many such global variables, but if they are fixed and you never need to create another variable again after that, you are probably okay. But if there are scenarios where you need more memory, but you already have a large number of global variables, you can actually run into problems. So there are a number of ideas that can be used over here. For example, you can use local function parameters instead of this concept of what is called global state. right? And global state is something that once again we will be talking about multiple times. Essentially everything which is in the memory of the system defines something called the state of the system, and how a program reacts to its inputs is a function both of the present inputs as well as of the overall state of the system, right. So this having a concept of global state where I have many parameters that are stored in different places but which contribute to the possible behavior of the program is something that can actually make your program difficult to reason about or to optimize, right. So in general it's always a good idea to try and minimize this concept of global state in a program. Instead of that, if you can sort of just have function local parameters that are used as and when required and then discarded once you exit the function, that's very often beneficial. And the other thing would be, you could also try and reduce the amount of dynamic allocation and deallocation. Dynamic allocation, dynamic memory, as we will see later, goes onto the heap in a C programming environment, and that tends to be the same area that global variables also are going to, right. And having these can actually sort of interfere with each other. You could end up in a scenario where you run out of memory eventually. So all of these not only enhance the modularity and reusability of the code, it also decreases the chance of bugs that are related to having global state and which would otherwise have been difficult to identify and reason about. Now loops and function calls, right, although they are obviously useful, right, primarily for the reason that they allow you to structure your program, in some contexts they can actually end up consuming more CPU cycles than you perhaps need to. And there might be scenarios where rather than having a loop or a function call which involves saving some data in a stack, creating a new stack for the new function, loading its parameters into the appropriate place and then jumping to the location of that new function, executing it and returning. Instead of that, perhaps if you just wrote out the function directly or wrote out the instructions corresponding to the function, there are scenarios where that turns out to be more efficient, right. Now an example of that, which is not hopefully not very common, is that you could have a scenario where you have a for loop, and inside the loop there is a function that's being called multiple times but with the same set of parameters. And if that happens, the simple solution would be take that function call, pull it out of the loop, execute it once before the for loop starts and just use that value internally. Now these kind of optimizations are in many cases automatically identifiable by compilers, right, and most compilers will try and apply them automatically, but it may not always happen, right, it's not guaranteed that it would be there. So these are things to sort of keep in mind as you write your code, right. So this is yet another strategy that you could keep in mind while writing your code. And one other thing which again is related to the idea of compilers is, keep in mind that at the end of the day you are writing C code, but you are also using a compiler to convert that code into assembly language which is specific to a particular processor. And there could be specific processor features. We will look at an example later. For example, for ARM processors there is a concept of something called bit banding, which is not generally available with other kinds of processors. That's something which you could write code which explicitly makes use of that feature of the processor, but without having to use something which is very specific to a given processor. If you know the right kind of compiler, or if you know that there is a compiler that is very well suited for a particular processor, you should probably learn a little bit more about what are the kinds of compilation flags or directives that you can give to the compiler that enable it to improve the performance of your code. One thing that is increasingly happening in different kinds of processors is that they have support for more computation in the form of what is called single instruction multiple data or vector operations, where you have one operation being performed on multiple data in parallel at the same time. So for example, if I had to add 4 sets of numbers, I might be able to give one instruction which basically takes 4 pairs of numbers and adds them all in a single instruction. In order to make use of that, you would need to have a compiler that can actually recognize your for loop which is going over these 4 data points and convert it into a single instruction that operates on multiple data. So the idea of using these built-in functions or compiler intrinsics is something where ultimately the bottom line is understand the tool that you are trying to use and try and make the best use of its capabilities. Now what we talked about so far are what are usually called strategies for improving the efficiency of the code that you write. There are also certain things which are usually called best practices, right? These are common patterns that have been observed to be useful over time by people who have written code for a long time. In some cases there may be very specific guidelines that enhance the security or the safety of a system, and in most cases they are not really mandatory. In other words, the compiler is not going to tell you that you have to write the code this way or it's going to fail, right? So it's not a syntax error to violate these best practices. They are recommendations, that's it, right? So in some sense they are similar to the idea of strategies, except that they could be a bit more specific and say that okay, write the code in this way and this usually helps. There are software tools usually called linters or lint checkers that are often used in order to provide suggestions on what can be done. Many of you may have already come across IDEs, development environments, including things like Replit, where you might have written C code, where as and when you write the code it sort of puts a squiggly red or yellow line. A red line is an indicator of an error, but a yellow line usually indicates that there's something not quite right over here or something not quite clear over here, and the compiler feels that perhaps if you wrote the code in a slightly different way, it would improve matters a bit. So a lot of these best practices are actually captured in linters. So once again, make use of tools like that in order to improve the quality of your code. So best practices, one of them is avoid floating point computations, right? Now what is floating point? The float data type in C, right? It basically uses a 32-bit value, but it sets apart a part of that 32 bits in order to represent an exponent, and the remaining bits are used for what's called the mantissa, which actually stores the significant digits of the number. Now these are very easy for humans to use and understand, but invariably they are actually hard for computers to use, right? In certain cases you might actually have a microcontroller that does not even have support for floating point, which means that if you use the float data type, it will still work, but it will have to emulate the behavior of floating point completely in software. That can turn out to be very expensive, many clock cycles, possibly hundreds of clock cycles for something as simple as adding two numbers together, right? So if you do have a scenario where you are working with numerical computations, try and use what are called fixed point computations. These are essentially integers which have been approximated to decimal values by using some kind of a scaling factor, right? They are harder for humans to understand because there are issues with overflow, underflow, normalizing the range and so on that are not very obvious and easy to use with fixed point. But the payoff can be very useful, especially when you consider the speed of the code that you finally get. Dynamic memory management, this is something that we will be talking about a lot more. There are scenarios like memory leaks, right, where you basically allocate a certain amount of memory and you do not free it in the right way, right? And after a while you find that the system has run out of memory. It either makes the system unstable, meaning that certain kinds of memory allocations fail, or it could outright crash and the system just says, I've run out of memory, I don't know what to do, and reboot or restart the system. There are a number of strategies that can be used over here. Typical would be to make sure that you track all your dynamic allocations and free them when required, right? And another one, which once again we will be talking about later, is use static memory allocation wherever practical. Right? Compiler optimizations and directives, I did sort of talk briefly about this earlier. These are settings that allow the compiler to modify the generated machine code, and usually they can be used either to improve the performance or to reduce the size of the code. For example, -02 is just a flag that's or an option that's given to a compiler while invoking the compiler. After all, a compiler is a program. When you run it, you give it an option flag that tells it what kind of optimizations to do. Minus O2 usually refers to speed. Try and make it faster by applying various kinds of optimizations. But minus OS says optimize for size. Try and make the resulting program as small as possible. These are things which, if you find that at a crunch your system is not able to run either fast enough or it doesn't have enough memory to do what you want, using these kind of flags can make a big difference to whether your system is actually usable or not. There are inline functions and macros, right? Macros, the hash defines that we have come across in C, are things which can actually significantly enhance the kind of programming that you can do. It allows us to, for example, if I don't have an absolute value function defined in my libraries, I can create one very easily by just replacing it with just conditions, right? When used correctly, these kind of tools, macros and so on, can give you a significant reduction in the runtime overheads, because these are all expanded at compile time and they directly translate into simpler code. But if you are not careful, they can also make your code quite difficult to read and understand. So they have to be used with care, right? There are scenarios where they make sense to use. There are scenarios where they can actually affect the readability and maintainability and even the performance of your code if you are not careful. Now, testing is something which we have looked at briefly in the context of the C programming. Which basically says that if I am writing a function, I roughly know what output to expect for a given input. You need to do this extensively, right? These are this kind of best practice comes from the domain of what's called software engineering. At some level, embedded C programming is a form of software engineering, right? And so knowing the tools of software engineering will definitely have a big impact on how you as a programmer or an engineer designing embedded systems actually approaches the problem at hand, right? So testing, unit testing, integration testing, system level testing, setting up mock objects, simulation environments, these are things which we will look at some level as we go through the course, but to some extent cannot really be covered in full detail in a single course, right? And are things that you need to sort of absorb through practice, right? But the important thing to understand is the best way to catch a bug in a program is to catch it as early as possible, which means that if you can test each and every single function as and when you write it, the chances of it actually having bugs when you integrate everything together and create a large program significantly go down. Okay. Profiling is another set of tools that end up being very useful in the context of how we actually identify resource intensive parts of the code. There are a number of tools, Valgrind, gprof and so on are things that can be used for finding memory bottlenecks, profiling bottlenecks, meaning that speed related bottlenecks and so on. In a lot of cases, the compiler tool chain that you have will give you specific tools that help you to identify such things, right? And they sort of tell you where to focus your optimization efforts to get the maximum benefit. Okay, so to summarize, just this last line is pretty much what it comes down to, right? There are a lot of tools that are available to you. This is engineering at its best in some sense, right? There is very little theory that you have over here. There are a number of best practices, things that you need to absorb, things that you can read about to some extent, but at the end of the day, the only way to implement it is actually write code. Okay, so on the other hand, what we are going to be doing through this course is to at least try and give you a flavor so that the thought processes are in place. You need to be able to think about or reason about a given style of writing code and say, okay, could this have been done better? What is the right approach to solve this problem, and so on.